So now we get to resolve the big cliffhanger that everybody, I'm sure, they've been hanging on this resolution ever since the end of the last lecture. We learned all about arithmetic coding. We learned about all of these interesting ways we can use real numbers in compression. But I'm sure all everybody can think about is how are we going to represent an infinite decimal expansion in some finite number of bits? That's what's been eating away at people. I'm sure you jumped right over here from the last lecture because you couldn't wait to find out what happened. You're binge watching the compression lectures. So we finally get to resolve that cliffhanger of how do we represent an infinite decimal number, a decimal number with potentially an infinite number of decimal places in a finite number of bits. And the answer is that we don't, because like every cliffhanger, the whole point of all of that suspense was as a marketing gimmick to get you to watch the next episode. You should know that by now, to make sure you don't tune out during the commercial break. If it sounds too good to be true, it's because it is. So we can't do this. I mean, the expansion of a real number, which could have an infinite number of bits, so we know that every real number has an infinite number of places, but usually if we're representing something that's got a specific number of decimal places, we assume that it eventually turns into a infinite sequence of zeros. But we know that even if we try and represent rational numbers with a decimal or binary expansion, the number of bits that we need, including the position of the last one bit, could be an infinite number of positions in the future. I mean that loosely. Infinity is not a number. So what do we do? Assuming that this is true, which I'm going to do for this lecture, what do we do? How do we get all the benefits of arithmetic coding without actually having to maintain an infinite number of positions? Well, the first observation is we were doing just fine using real numbers in the arithmetic coding lecture, despite the fact that those real numbers, spoiler alert, did not have an infinite number of decimal places of precision. So maybe there's a remedy. We just have to be a little bit careful about this. And we have to consider the fact that although we have plenty of ways of representing real numbers on computers that don't obviously have infinite precision, those are still not going to be great for this. There are some things that those have that we don't need. So floating point numbers, for example, have an exponent term that we don't need to use at all. So they have the ability to scale up and down to minute values or to very large values. When we want to keep things sitting around zero, we want to keep we want to be working with a decimal expansion of something between 0 and 1. But they also, of course, have a finite number of bits of precision, and we know that what we ultimately need with our arithmetic coding is the ability for that sequence of bits to go on for a very long time, far beyond the fixed precision we would get with a floating point number, whether it's float or double or long double or whatever. So let's take a look at this. Let's actually think about what happens if I look at an incredibly long binary expansion, just for the sake of putting ourselves in the right mindset of setting the stage, I guess. So arithmetic coding, as we've defined it already, I guess this lecture, I made these slides before I changed my mind about the capitalization. I think I've uploaded the arithmetic coding slides. I've already changed all the capitalization. So nobody would ever believe you if you said that I didn't capitalize those things before. We saw already that the way we've described arithmetic coding so far thinks of real numbers in their pure conceptual sense, as pure mathematical objects. We don't have to deal with the realities of representing them in a computer. And so the reason why we care is that we have these values low and high, and we keep performing operations on them over the course of the algorithm. And we know that if we're not careful, little bits of error that might pile up could affect the accuracy of computation over time if we use insufficient bits of precision. And the reason we care is that we ultimately want to emit our finished encoding as one number, basically, as the bit sequence that forms one single fractional binary value. Now, first observation is if I encode this sequence, the first character is A, and so I encode the probability is 0.33, and the cumulative probability window is 0 to 0.33. And just to make it clear, this is actually 0.33 repeating because it's 1/3. And you'll notice that even though I've only encoded one thing, the binary expansion now actually already has an infinite number of 1 bits. So there isn't some position at which every bit after that position is going to be a 0, because the value 3, 1 over 3 doesn't, 3 and 2 are relatively prime, so we end up already seeing this problem, where if I truncate this any number of bits, it ceases to be the value 1/3. And you might know that already from numerical analysis, that we are able to get away with quite a bit of valuable arithmetic operations, despite the fact that if we cut the number off at some number of bits, we're losing accuracy. And it turns out that the same is actually true here. We actually know that already because the computations we were doing last time in the previous lecture, we lost a bit of precision here and there, way off the end of some finite number of bits, and it didn't seem to hurt us too much. So just to be clear, it's actually fine to truncate. This is not the value 1/3. It's close to the value 1/3, but it's been truncated. And depending on how we view that, and I'm going to view that as when you truncate a number, we just assume every bit that comes after it off to infinity is a 0 bit, then the value of high is actually a little bit lower than it's supposed to be. I've truncated it down. And it turns out that this is actually fine. There's an error that I'm introducing by doing this. We just need to make sure that the error is so far off in the distance, it's so far away from where the action is happening, which I would argue is sort of around here in this case. It's around the place where the bit sequences first disagree, where the first bit that's different between them. As long as the error we're introducing is pretty far away from that point, the only real disadvantage it can introduce is a compression efficiency disadvantage, which is to say the errors do like the small number of bits that I lose can result in the range being a little bit bigger or a little bit smaller than it would be theoretically in the sort of pure mathematical sense. So in the pure mathematical sense, the amount of real estate that A should get is 1/3. But if I truncate this value down to what I had a minute ago, then the real estate is not actually 1/3. A is a little tiny bit underrepresented. It's incredibly insignificant if you think about how many bits I'm staring at between the place where the action is happening and where I did the truncating. But there's a tiny error being introduced there. And just like Huffman coding, there is this issue when you deal with things like this in a finite setting that you do introduce what amount to rounding errors one way or the other. The issue is in arithmetic coding, we have more control over how those errors are introduced, and we'll discover that they're pretty insignificant compared to what happens with Huffman coding. Huffman coding has much less granularity in how the error is controlled. So not that you have to have done this, but if it's the case that you've taken CSC 349A, you might know already about the various forms of numerical error that we can work with. We're not going to really talk about them in that sense. We just need to know that they're in the background somewhere, and that just like in 349A, if we know what we're doing, we can pretty much avoid those being too severe. So there are certain operations that can result in really terrible errors occurring, so subtractive cancellation or something. But in the background of every numerical computation is the fact that you're losing something way off the end. If you have some finite sequence of bits representing an infinite value, then if you need the bits that are down here, you're out of luck. And the trick is to use numerical algorithms that don't, where the amount of error that we end up getting out of the result of the algorithm is not compounding to some exponential sense the error that came in, I guess. It's fine for there to be error going out. It's actually even fine for most algorithms to produce the amount of error that comes out might be bigger than the amount that goes in, because over time errors can pile up. We just want to make sure that the piling up is relatively slow. It doesn't exponentially increase. And so it turns out that the errors that we're willing to put up with are ones that affect efficiency. So if the range is not actually truly 0 to 1/3, so in other words, I want the range 0 to 1/3. But if I end up with the range 0 to, I don't know, this value, which is not 1/3, I'm willing to put up with that. As long as the magnitude of the difference is significantly smaller than the magnitude of any particular symbol's probability. Notice that here, the error that I'm getting, but so 1/3 minus 0.3333 is, well, it's 0.0000333 repeating. And I think, okay, this is a number, yes, and it is, I mean, it's a positive value. I'm losing some range there. I have an error. But if I compare that to the probability of each symbol, it's pretty tiny. So the error is significantly smaller, several orders of magnitude smaller than any of the numbers I'm actually working with in the algorithm. These numbers, of course, translate into the widths of these ranges. And so in this case, of course, the error is even smaller still because I'm truncating after dozens of bits. And so I'm willing to put up with that because, yes, there's a small error. I'm losing a bit of real estate here, gaining it somewhere else. But it's not the biggest deal because it's far below the significance level of the probabilities that I'm working with. Now, if I had probabilities that were on the order of 0.00001, then I might need to be worried here. And we'll discover that our rule of thumb is just choose a precision level that gives you significantly more bits than the significance level of the probabilities you're working with. And we'll demonstrate that in a minute. So actually, no, we're doing that right now. I guess I forgot the order of these slides. So here are the equations in our encoding algorithm from last time that update our bounds. Just for the sake of resolving ambiguity, I'm calling the actual equation is just low equals low plus this. It's an update to the variable low, but we'll call it low and new low. So what I need, basically, is enough numerical precision that when I've updated low and high, they are still far enough apart from each other that I can tell that they are endpoints of a range. That's actually all I need. I don't want to end up with so little precision that low equals high, because then I've got a problem. I need a range that has some room. Ideally, I need a range with enough room that I can actually do work at my next step. But really, the baseline requirement is I need to make sure that low is never equal to high. That has to apply no matter what symbol I'm encoding. Certainly, the range that I get at each step, the size of that range depends on which symbol I encoded. I know that the range will be smaller if I encode a symbol with a really small probability. I need any range I could end up with at the end of each step. So when I start the step, no matter what symbol I encode, I have to be guaranteed that when I'm done, the range that I'm left with is big enough to do actual work, to continue the process. And we can reduce that to basically, it's sufficient for low to not equal high. It's true that if low is equal to high minus 1, we're going to have a problem at the next step, but they're still different, and so there's still room between them. And we know, obviously, that if I'm only keeping things to 5 decimal places, and I end up with a sort of degenerate case like this, 1, 2, 3, 4, 1, 2, 3, 4, 5, I guess, and for some reason low and high look like this, this is not ideal, but they are different. And although it looks as if I have to cram everything into 0.00001, remember that there are an infinite number of values between 0.12345 and 0.12346. So I actually have room there. All I care about, frankly, is having that room and guaranteeing that I'll still have that room at the end of the next step too, which isn't going to happen if I'm not careful. There are two sides of that coin. So what really I'm saying is at the beginning of each step, if I assume the range is distinct, so low is not equal to high, I need to guarantee that no matter what symbol I encode, low is still not equal to high. And all that says is basically no matter what symbol I encode, there should be some dots here. No matter what symbol I encode, the resulting range is distinct. What I'm actually saying is if I take all the possible low values, and the reason that I don't have to worry about C high here is that C high of S1 is C low of S2, and C high of S2 is C low of S3. All I actually have to ensure is that if I were to compute all of the possible updated bounds, that set of numbers is all distinct. That no two elements from this collection are identical. That's actually all I need. I need enough precision to guarantee me that at every step. But you can think the issue there is that as the steps go by, low and high get closer and closer together. Eventually they're going to converge if I only have some fixed amount of precision. So I have another problem I have to solve. But the basic idea is I just have to make sure that at the end of each step, low and high are still different values. Now, I can actually fiddle around with this assumption a bit. Like I can fiddle around with it by doing algebra. What I'm saying is basically, if this set of values is distinct, we know that means that this has to be less than that, which has to be less than that. They're never going to be equal to each other. And we know that because of the way cumulative probabilities are defined, they actually fall into order. And so all I'm really saying is, for all I, this has to hold. The adjusted bound for C low of Si has to be less than the adjusted bound for C low of I plus 1. Now remember, when you look at this appears to be a tautology, and it is for real numbers. If I talk about real numbers, because of the definition of cumulative probabilities, if the probability of symbol Si is non-zero, this is always true. Remember that I'm talking about whatever representation I'm using. So if I'm using a representation with a finite precision, even though this is true in real numbers, it may not be true for that representation. So I need a representation where this fact is still true. If I do some algebra, it turns out all I'm really saying is that in my representation, assuming that we control for numerical errors that happen during the algebra that I'm doing here, in my representation, the current size of my window, high minus low, multiplied by every probability is still greater than 0. So there is enough precision to represent the product of any probability, for example, the smallest probability, and the current window size. So I could use this to actually figure, if you give me a probability distribution, we know that this is going to be the worst on the lowest probability. I could just use this to work out how many bits I need for that number to be non-zero, for it not to sort of round down to 0. So we actually have a way of solving that problem. We don't have a way of solving the problem of, as the encoding goes on, we know that low and high get closer together, their difference becomes smaller, and if I have a fixed number of bits of precision, eventually I'm going to run out. I'm going to run out of room. What do I do in that case? So I have to figure that out too. So let's keep running through this example and assume that as input size increases, the number of bits I need will increase linearly. That's a very weird thing to say. We're doing compression. I'm compressing an n symbol sequence, and I'm making the claim that if I'm compressing an n symbol sequence, the size of the output grows in proportion to n. Isn't the point of compression that the output grows slower? Well, yeah, but not asymptotically slower. You can't really assume your compression, even if you could always compress things, which you can't. Even if you could always compress things, you can't reasonably assume you'll be able to compress n bits into log n bits. And so the compression that we get, generally speaking, is still proportional to our input size. Maybe it's our input size times 0.75 or something, but that's still linear. So the number of bits increases linearly, and that means if I have a huge number of input symbols, that I'm going to run out of precision eventually. No matter, I mean, you give me a specific length of your floating point representation, and I will be able to find a number of symbols that exhausts it. So I've got a problem there. If I just say, I'm going to have every number be represented as a decimal value of like 64 bits or 50 bits or something. And so I need the ability to choose some fixed number of bits and somehow yet not run out of precision. So what I'm going to call your attention to is this red sequence that's sort of washing over my low and high values. So as the bounds get closer together, their leading bits converge. And this is a significant observation. So as arithmetic coding progresses, and this is true in base 10 and in base 2, low and high get closer and closer together. And low and high will therefore share some of their initial bits. The difference between them will only be reflected in the lower order bits as time goes by. The other observation to make is that if at a given step low and high have these bits in common, let's redraw that. If they have these bits in common, what happens to low and high during the next step? Well, they're moved, but they're moved closer to each other. The new values of low and high are always between the current values of low and high. And so if both low and high have these places in common, any number between low and high also has those places in common. And that means no matter how I update low and high, if they already share this number of leading bits, they are guaranteed to share this number of leading bits at the next step as well. In other words, once their leading bits match up, they will never change. And over time, more and more leading bits match up. We can see that here we had this number, we added 3 more. And it might be at a given step that no new bits are added. And we can see quite a few steps happen here where no new leading bits are shared. And then suddenly at the next step, they end up sharing this number of leading bits. And the key is at this step, as of this step, for the entire remainder of encoding, no matter how many more symbols there are to encode, these bits will never differ between low and high. The interesting jump we just saw where for some reason, even though the number of bits was increasing sort of regularly, and then we began saving them up for a few steps and then it suddenly jumped, that's actually a different issue we're going to have to deal with later. We want to be able to rely on the number of bits that are shared between them sort of increasing with some regular frequency. So if that's correct, I mean, just what I just said was an explanation. Just like before, we can't just believe what people put on slides. We have to we don't have to write a proof. We have to at least justify this mathematically. But assuming that that's correct, then we don't really need to store those shared bits. I mean, really, once these two sequences are shared between them, do we really care anymore? In fact, arguably, I could just output this sequence. This is the beginning of my compressed number. Just output it. Send it to the output and never look at it again. Just ignore it. I could save the bits that I'm using for the interesting stuff, the stuff that's actually different between low and high. So I want to justify the observation that I just made. So the fact that once the leading bits agree, they're never going to disagree. And basically it comes down to, we certainly know that if we have low and high sharing n bits at the beginning, any value between low and high also shares those n bits. The issue we have to justify here is we modify low and high at each step. How can we be guaranteed that the modification sits between low and high? And if we stare at this, what we can observe is if we rearrange terms a little bit here, what we end up with is, I'll rewrite the equation for new low. It's low of 1 minus C low of Si plus C low of Si times high. And C low of Si is a cumulative probability, so it's between 0 and 1. And that means what we actually have here, if you notice, is if we've got an equation of the form, there's lambda times x, and there's 1 minus lambda times y. We have what's called a convex combination. And if you take a convex combination where the underlying x and y, so that's high and low respectively, or whether one's less than the other or the other one, like as long as you have lambda and 1 minus lambda, then the result will always sit in the interval xy. And so it's true that if low and high already shared a bunch of positions, that the results of updating low and high will continue to share them because the results of updating low and high will lie between the current values of low and high. And so, as a result, the observation is true. We can justify it with this convex combination. And therefore, once the two binary expansions have a common prefix, any new bounds we compute at this step or the next one or the one after that, going as far forward into the future as we want, will share the same common prefix. And therefore, if we no longer need that common prefix, we could just throw it out. We could output it, because we're going to need it at the very end, but we don't need to do any more work with it, and it's never going to change again. So we could output it and then save our bits for something else. So we can combine the observations to produce an arithmetic coder that uses fixed point arithmetic, not floating point, so it uses a specific number of significant digits, and where I avoid locking down my bits with this common prefix by just outputting the prefix as soon as it forms. Every time I notice that the two sequences share common bits at the beginning, I just send those to my output stream and then shift them out of the string. So remember that the bit string itself is this. The 0 point is just a notational device. I'm only storing the bits after the decimal point. Okay, so here's a probability distribution. The smallest probability is this value, and we'll notice actually this is a continuing fraction, but we've already, I guess, justified that it's okay if we truncate that as long as we leave a decent number of bits between after where we're actually doing work. So 0.083, I'd say if we keep this much of it and we truncate it here, so the action's probably happening usually around here. So truncating it there shouldn't be a big deal. The first thing I want to observe is that whether or not it's a good idea to truncate it, we could always avoid actually doing the arithmetic. This value, 1 over 12, is two integer value. It's a rational number. It's two integers. I could do division to compute some fixed point representation, but do I have to? I don't need to do it yet. I will need it eventually, but do I need to do it now? Probably not. Even if I could truncate it, I could just compute a table of cumulative frequencies instead of cumulative probabilities. So instead of caring about the probability line, I'm going to care about the frequency of each symbol and, more importantly, the cumulative frequency of each symbol. And if I ever want to convert a frequency to a probability, that's actually pretty easy. All I do is divide by the total frequency. So in this case, the size of my input data set. And that would just be the sum of this row. And actually, conveniently, the highest cumulative frequency bound, this thing, the cumulative frequency, the high end of the cumulative frequency bound for the last symbol is also going to be the total frequency across all symbols. So what that means is that I'm going to define, notationally, I'm going to call CF cumulative frequency, not cumulative probability. and the cumulative frequency is always a value between, it's an integer between 0 and the total number, the total sum of all frequencies, so not between 0 and 1. And I can always convert that to a cumulative probability by just dividing it by this value t, the total of all frequencies. The same way that I would compute probability from frequencies by dividing the frequency by the total of all frequencies. Okay, so how am I going to represent my low and high values? I said fixed point, but what is that supposed to mean? What I'm going to use is, if you hand me a bit string, so there's an example down here, but I'll talk about a different example. If you hand me this bit string, so a 6-bit number, I am going to treat this like an integer, just to be clear. But so I'll do integer arithmetic to it. For example, I could take this number and I could, so this is x, I could say x plus 1, x is an integer here, x plus 1 equals this value, 101110. So just to be clear, these are actually going to be treated as integers. If I ever want to interpret them as a fractional value, I'm going to write, I'll do it down here, fr of x plus 1, and I have to say how many bits I'm using. I guess I'm using 6. That equals this binary fraction. So it's taking all the bits of my value x and sticking them after the radix point. That's it. So I actually want to talk about both of those things. I want to have an algorithm that can work with both this integer value that's storing a bunch of bits and do arithmetic on it if I want to, and the interpretation of that integer as a binary fraction. And so I'm going to use, I just made this up, I'm going to use this notation. FR sub 4 means assume it's a 4-bit number. That's significant because if I tell you you have this number and I say treat this as a binary fraction, well, it depends on how many bits the field is. If the field is actually 6 bits wide, the binary fraction is this. If the field is only 3 bits wide, the binary fraction is this. So just giving you the bits isn't enough to tell you what the fractional interpretation is. So if low, suppose I'm using 4 bits, if low is this set of bits and high is this, then those are integers. That's the number 6 and that's the number 11. But if I want to interpret them as fractional values, I will use this notation. FR of low equals, well, just take the bits, put them after a radix point. It turns out that's equal to this. Who cares? I mean, for the time being, who cares? But we can evaluate it like any other fractional value. Now, this representation gives us a couple of interesting properties. So one of them is, I'm going to go back to my previous example. X is this binary string in 6 bits. And the question is, okay, so x plus 1 is just adding the value 1 to the lowest, to the least significant bit. So it would be 101110 in base 2. My question is, what is the fraction? Is there a relationship between arithmetic that I'm doing on the integer representation and the fractional representation? And all I want to point out is that if I take fr, sub 6 of x plus 1, that actually equals, so that equals 0.101110. That actually equals 0.101101 plus 0.000001, which equals the fractional representation of x plus 2 to the negative 6. So that's an odd observation to make. The reason I care about that is because if I want to operate on positions of my binary fraction, I can now just do integer arithmetic. I don't actually have to do any funny floating point stuff. And it turns out you can also demonstrate that if I compute the fractional representation of adding 2 integers together, it's the same as if I added their fractional representations. That's a big deal. And if I compute the fractional representation of multiplying 2 values, it's the fractional representation of one of them multiplied by the other treated as an integer. So it's not symmetric. You have to, one of them does not get treated as a fractional representation. It turns out you can choose which one, but one of them has to be treated as an actual integer. The reason why that's significant, though, and I'm just going to leave this here. So much of this lecture is for completeness. I should have mentioned this at the beginning. I will post some code that implements the algorithm we're ultimately dealing with here. The justification for the algorithm I have to cover because I feel I'm duty-bound to do it. But much of this stuff is not actually, we don't care too much about the nuances of this because it's not really compression. It's mostly numerical analysis or something similar to that. We just need to know what's going on. So this last identity is really important because it means later when we need to write the arithmetic coding algorithm, I can actually update my fractional bound, my value of low and high, without actually doing any weird fractional arithmetic. I just do integer arithmetic using so cumulative probability C low is equal to cumulative frequency divided by T. And it turns out that if I have my bound, like if I is the low, my low bound, then this expression, the thing I would normally be computing to update it, I guess in this case I would be the range of the bound, ends up just equaling this, which is what I want. So there's one issue with this, which is if I say, and I'll write the same thing out again, x is this value, then the convention I've established is you take the bits of x, the fractional representation is the bits of x after a radix point. So how do I represent the value 1? Well, I don't, because the 0 point, that's dictated in all cases. If you have an integer value, its bits come after the radix point. So what do? I do occasionally, like once, I need the value of my upper bound high to equal 1.0. At the beginning of encoding, it does that. Usually, not always, usually it's reduced afterwards. Not always, because it could be that high stays at 1 the whole time and low approaches it from below. So it doesn't happen, I mean, I don't need it for every step, but I do need some way of representing the value 1.0. And there's a couple of other issues I have to address, but the 1.0 is one issue. So how am I going to do this? Well, there's a lot of alternatives. I could just add an extra bit to my encoding. That's a bit wasteful. And it turns out that, so what I mean is I could say, okay, you're using 6 bits for this. Let's just use 7 bits and have the most significant bit now be a 0 or 1 to tell you if you're working with the number 1. That's undesirable because it's sort of a waste of a bit, because I'm never going to have 1.5. I'm only going to have 1.0. But also because there's a certain advantage to having the width of my integer field be exactly as wide as my expansion, because that means if I shift bits off the left, they just disappear. If I have a 7th bit there at the beginning and I do a shift, then I have to worry about that 7th bit. And we'll notice that bit shifting really helps us later. So there are a couple of reasons why I want to come up with some interesting out-of-band solution to represent the value 1.0. So here's the way I'm going to play that. I'm going to observe this wonderful way that a good way of trolling first-year students or whatever is to get them to start arguing about this issue. 0.9 repeating, and this is in base 10. So 0.9 in base 10, which is equal to 0.99999 ... an infinite string of 9s. As you all know, that is exactly equal to, not approximately, exactly equal to the value 1.0. It is a case in our numbering system of there being 2 representations that are equally valid of the same number. A lot of people, there are many fringe theories out there, and people that like fringe theories that don't necessarily agree with the commonly held beliefs about, let's say, the topology of the Earth or something similar, might think, oh, these are 2 different numbers, it's a conspiracy, whatever. That's lots of fun. If you want to argue about that, come to the office hours. It'll be fun to do that. But these 2 things are equal. And it turns out that, in fact, that identity maps on very well to base 2. It turns out that this value, the value 11111 repeating, 0.111 repeating, is actually equal to 1.0. Now, it's neat because you can prove this using an identity from 225. So, not that we need a proof of this, because we shouldn't need to reduce ourselves to proving things like this. But it turns out, what is this actually equal to? Well, let's just evaluate each decimal each binary position. So it'll be I'm spoiling it. It's 2 to the negative 1 plus 2 to the negative 2 plus 2 to the negative 2 to the negative 3 plus ... to infinity, which is this sum. And well, just to make it more clear, which is sort of a well-known geometric series that you can verify sums to 1. So that's equal to 1. Great. Okay. So what I could do is I could attempt to say, well, hey, I know that 0.111 repeating is equal to 1.0. So why don't I try something sneaky, like have my high value be equal to a sequence of all 1s? Because, that's equal to 0.1111 But the problem is this is not equal to 1 because it's not an infinite string of 1s. It's a finite string of 1s. That's a different value. And so, unfortunately, our secondary fact here doesn't give us exactly what we want. So I'm going to have to try some other technique. So to be clear, the remedy we use is inspired by this, but actually is not this. What I'm going to do is I'm going to observe that the problem that I have is because it doesn't matter, it's not a fractional precision problem. It's that any representation with a countably infinite set, I mean, like even if I'm using bit strings of any finite length or whatever, I'm trying to really essentially map the real numbers onto the integers. That's my issue. And the way that I have to work around that is I have to think a little bit like I have to not attempt to ascribe properties of real numbers to anything that can be stored as an integer because it won't work. And the issue is the way that a half-open interval has to work in real numbers doesn't map on well to the integers because of the age-old problem that if you choose any two real numbers, x less than y, no matter how close together they are, there are always an infinite number of values between them. That's a classic property of real numbers that does not hold for integers, even though there are an infinite number of integers. And so what I do instead is I represent my value high as this. I do represent my value high as a sequence of all ones, but I do not use it directly in my window. So instead, I take the position that my probability window will be this. High plus, and actually, okay, I should be very careful about my notation here. My probability window, of course, will be the fractional interpretation of low, and the fractional interpretation of high plus 1. So I take my integer value high and I add 1 to it. And then I take the fractional representation of that. And I will observe that if I take 0.1111 plus 0. So a 0 all the way to the last position, that equals 1.0. Even though I can't represent 1.0 directly, I could adopt the convention that the number I represent as my high bound is always just one less than the actual upper bound if I express the bits in terms of integers. So I do that. So what we're basically saying now is that the interval I'm storing is no longer a half-open interval. It's not as simple as saying it's a closed interval because there actually is some room between high and the true upper bound, which I'll get to in a minute. So the original interval, in the original algorithm, these two values low and high, low is the lower bound of the interval and low is included. High is the upper bound but is not included. Formally, it's the smallest real number not in the interval. You can get infinitely close to high and be in the interval, but high itself is not. We can't really duplicate that logic with integer valued representations, no matter how we phrase them. So instead what we do is we just change. We attempt to represent high using as many bits, like using all the 1 bits we can, and then take the position that the interval is low to high plus 1. But that doesn't mean that there's no distance between low between high and high plus 1. And I guess the point that I'm trying to circle around here is you could stare at this for integers and you could say in integers, the open interval x to y plus 1 is exactly the same as the closed interval x to y, right? If it's every number from x up to y plus 1, not including y plus 1, what you're really saying is it's every number from x up to y. This is not the case in real numbers, and it's not the case in this either because this is an attempt to represent a real valued interval. So I can't say that, okay, it's easy. My interval is now just fr of low up to fr of high inclusive. It's certainly true all of those values are in my half-open interval, but there are some values not included in there that are still in the half-open interval. And in particular, if we think about this, so suppose my high ends up being this value here, this integer. Well, that means that the actual endpoint of the interval is this, 0.1100. But just to be clear, every value beginning with this expansion, every binary value whose first 4 bits are this, will be less than the true upper bound. And that means every binary expansion beginning with my high value will actually be in the half-open interval. So there are values bigger than this number that are still less than the true upper bound of the interval. Okay, that's a lot of stuff, and I had to carefully choose my words to avoid turning this into a real analysis class or something. It turns out it's not that big of a deal, except that this quirk results in a bunch of -1s and +1s showing up in my arithmetic. Because my arithmetic is designed for working with the true low-high interval, but if I ever want the real high value, I have to add 1 to something or subtract 1 from something. And so we'll notice in the eventual pseudocode that we see a lot of +1s and -1s. And so here's the first round of that. So if I want to compute the actual range size, high minus low, I actually have to do high +1 minus low. And so one thing a bookmark I'm going to place here, the slides are going to mention it in a minute. If we've chosen a certain number of bits of precision for low and high, suppose you decided low and high are stored in 16 bits, then this lecture is given under the assumption that all arithmetic you perform, even if you're guaranteed, the size of my range will always be, my new high and low values will always fit into 16 bits if low and high are 16 bits. But there might be intermediate calculations that require more than 16 bits. So the implicit assumption here is that if you've chosen 16 bits for low and high, you use 32 bits for every calculation you do on them. When the calculation is over, the result will definitely be inside 16 bits. That's fine. But anything you do in the middle might go over. There are other ways of doing this where instead we guarantee that all of our values we use 16-bit variables, but make guarantees like all of our underlying probabilities or something are less than 14 bits. But we still need to make some assumption about the number of bits used by values. I think it's easier to say we'll choose a storage size for our data, let's say 16 bits. Or 32 bits, and then we'll do all of our calculations in twice that amount of precision. Okay, so why twice that number? It's basically to play it safe. It's because if I take two numbers that are n bits and I multiply them together, I could get a 2n bit number. And so because of this idea that our high value is actually 1 less than the true end point of the range, then every time we need to actually compute any statistic based on the range, we have to add 1 to our high value. And in this case, because my arithmetic is being done in more bits than my storage is, I can add 1 to high, even if it's a string of all 1s, and I get something that I can work with. And then to compute my new high, what I do is I take my range, which is using the true value of the high end, and I multiply it as I would before. You might notice that the original equation was range times the cumulative probability. Here, I'm using cumulative frequency. And I could write that as range times CF over T. But instead, I've written it as range times CF all over T. And the reason is because if I do it this way, I am not running the risk of bottoming out. You could call it underflow, you could call it cancellation or truncation. There's a numerical problem that I have with fixed point arithmetic, which is that CF divided by T could end up just coming out to 0 if CF and T are both stored as integers. It could be that CF is less than T. In fact, I expect it to be less than T because I expect this cumulative probability to be less than 1. So if I want to avoid everything just getting slammed to 0, if I want to compute something like this, I should first multiply everything on the numerator to make a large enough number that when I divide by T, I don't just get a 0. So that's what I'm doing there. That again is not something that's that relevant to this course. It's sufficient for this course to just believe this formula. I want to do my due diligence anyway and give you reasons to believe it. Explain it to you whether or not it's going to be on the exam. And then just to be clear, this -1 is because this range uses high plus 1, but I'm computing my new value of high, which of course I have to then subtract 1 off of because it's 1 below the true upper bound of the range. So we'll see +1s and -1s showing up in all sorts of weird places as a result. So let's try using 16 bits for this. And I want to explain the key reason why we've made all these decisions. Okay, so the first one is, and just to put another point on this fact is really powerful. So I've given a few different excuses for why I'm not storing the true upper endpoint of my range, why for some reason the upper endpoint is high plus 1 and not high itself. One thing that we're going to notice that really drives the point home is if high equals 1011, then every bit sequence beginning 0.1101 dot 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 is always in the true range. I should be using FR there. So that's what the slide is saying, but I can't emphasize that enough. No matter what bits I stick on the end of that sequence, they are still in the true range. So the question is, what is the largest value that actually is in the true range? And I mean largest in a real number sense, not in terms of what I can represent. Well, let's see. What's the largest value whose bits are prefixed by the value high? Well, it would be this followed by an infinite sequence of ones. But I can actually think about that. That is something I can conceptualize. If I stored the true upper bound of the range, what would be the largest number actually in the range? That's a really hard thing to conceptualize with integer arithmetic. But here, because what I'm storing is just a little bit less than the actual upper endpoint of the range, I know what the true upper endpoint of the range looks like. It's an infinite sequence of ones after that. Or, well, okay, sorry. It's a sequence of ones as long as I need for my calculation, beyond the precision of my variable. An infinite sequence of ones would actually end up equaling this number. So okay, we're going to swerve here to avoid it turning into a real analysis class again. So, okay, let's take a look at what we end up with. So this is assuming, it's not the only way of doing it, but it's an assumption we can easily satisfy on modern hardware, that if I choose some number of bits, like 16 bits, or 32 or 64, if I choose some number of bits for my storage of low and high, that all arithmetic that I do is done in 32 bits. The equations will result in me getting a 16-bit result eventually, but the intermediate computation might exceed 16 bits. So everything will break unless you abide by that assumption if you use this variant of the algorithm, the one I'm presenting here. Okay, so at each step, I compute those formulas, the ones I showed earlier, the revised ones for this, and then I take a look at the new low and the new high value. If I discover, and maybe I don't, but if I discover that they share any common prefix of bits, here's what I do. I take each of those bits and I output it. Okay, so now my compressed bit stream now has one bit in it. Then I remove those bits, so I shift everything to the left to remove those bits from low and high. So they're no longer there, they're no longer eating up space. And then, of course, because I shifted them, I have to fill in the bit that I shifted in. So for low, I shift in a 0 bit. Because, of course, if my existing thing was, if my old value of low was the lower bound, adding a 0 to it means it's just equal to that. For high, I shift in a 1 bit. Because the old value, because we know, because of what I just said a minute ago, a sequence of ones on there is still going to be inside the range. No matter what bits I stick on this high value, I'm still inside the range. So I shift in a 1 bit to keep the range as big as possible. So I always shift in a 0 to low and a 1 to high whenever I do this. And we can see I've illustrated the shifted in bits in blue here. And the number of bits I shift in each step is equal to the number of bits I shift out, obviously. Okay, so I keep going. And here, I managed to shift out 3 bits. So I get rid of this 1, 0, 0, and I shift in 3 zeros on low and 3 ones on high. And because I know that low is less than high, the shifting guarantees that when I'm done at each step, so after the shifting is over, the first bit of low will always equal 0 and the first bit of high always equals 1. Because the first bit of low will never be 1 unless the first bit of high is also 1, because otherwise high would be less than low, which is impossible. If the first bit of low is 1 and the first bit of high is 1, we would shift it out, like what happened here. If the first bit of both is 0, we would shift it out too. So by the time I'm done my shifting, which will be significant later, by the time I'm done my shifting, I am absolutely guaranteed that the first bit of low is 0 and the first bit of high is 1. Now, this helps a lot because you'll notice that because of this shifting that I'm doing, I am avoiding bits in my representation being locked down by the common prefix. I'm eliminating it, so I'm freeing up bits to be used by my calculation. Now, it doesn't eliminate the problem completely. There's something else that can happen that can't be eliminated just by shifting out the common prefix, where the bits can become locked. And the lock is temporary, but it could go on for long enough that all of the bits get locked, and then the computation fails. If at any step the range at the high ends up equaling low or something, then the computation has failed. And it turns out the second problem we have to solve in a minute will be called underflow, which is where the bits get locked up temporarily, but we'll get to that in a second. So we keep going through this. We'll just skip through this example. I want to observe that there are steps when no shifting occurs. That's bad luck. There are steps when tons of shifts occur. And we saw an example a few minutes in one of the earlier slides before we talked about this variant, where a huge number of bits suddenly matched at one step. Here, yeah, this is putting a bookmark here for later. This step, something very odd appears to have happened, where apparently low and high only share 2 bits, and yet for some reason I pushed 6 bits to the output. I contemplated excising this from the example, but no, there it is. It's doing something we haven't seen yet, and we'll get to it in the next part of the lecture. Okay, so I get to the end of encoding. So this is the end after the very last step. I have this. I'm not doing another step, but my low and high are this. My compressed bit stream is this. Now, the thing is, my compressed bit stream isn't done yet, because obviously my eventual chosen representative will be some number between low and high. And conceptually, the value of low is all of these bits plus all of these bits. And the value of high at this step is actually all of these bits plus all of these bits. I mean, the compressed bit stream, that's just the common prefix that both of those numbers share. It is still part of both numbers. And so I have to choose some representative that begins with this, just like low and high do, but is some number between low and high. And there's a few ways we can handle this. I recommend the following clever trick, which is I need some bit sequence. I mean, I could just say, look, if I want to output some number between low and high, just take all of these bits and add them to my compressed bit stream. That would work, right? Like then you'd have a representative that's definitely between low and high, because we know that if you add an infinite sequence of zeros to the end of low, you're still between low and high. I could do that. That would require increasing my compressed bit stream by 16 bits. Is there a better way? And my observation is that, well, low will always begin with 0 and high always begins with 1. We saw a minute ago that after the shifting is done, these two bits have to differ. So if high always begins with 1 and low always begins with 0, then doesn't the string 0, 1, 1, 1, 1 off to infinity, doesn't that string lie between low and high? I would say it does. So here's the trick I'm going to do. I'm going to assume that the decompressor, once it sees the end of my sequence, will repeat the last bit forever. So if it needs any more bits than I give it, it will just assume to take copies of the last bit. So if I just tack on 0, 1, the decompressor will then, if it needs any more bits than that, will just make copies of the last bit off to infinity. And so because of that, I could just tack on 0 and 1. As long as the decompressor remembers that trick, I don't need to add any more bits besides 2 extra bits in all cases. Now, if you don't have that luxury, you'd have to add a few more 1 bits or something else, or you could just dump the entire contents of low. I guess you only have to dump it up to the first or the last 1 bit, because we can assume after it is an infinite sequence of zeros. So in this case, I'm just going to append 0, 1. And then I will and we'll agree in advance, compressor and decompressor, that the bit stream I send you will be a bunch of bits, and after the last bit, you just repeat the last bit or a 1 bit forever. It turns out repeating a 1 bit forever is actually somehow more difficult, as you'll see in the code that I post. It's actually more difficult for the decompressor to do because of byte alignment than just repeating the last bit that was read. So we have one more problem. And this is something, again, for this course, I have to explain it because I wouldn't live with myself if I didn't explain it. We don't care that much about why many of these things occur, unless for A3 you choose to go deep down the route of developing a new style of arithmetic coder. Probably you'll want to use arithmetic coding, but you probably won't care. You'll probably focus instead on how the probabilities are modeled, not so much how the bits are output. But let's talk about this one last problem. To show this problem off, I need a really weird-looking probability distribution. It's sort of synthetic. These distributions do occur in practice. The issue is that you need a pretty long input to make them appear. You need a pretty huge amount of data, because normally we compute our distribution based on the characters in my input string. because I just want to show the problem off, I'm going to encode this string here, but I'm going to use this distribution to encode it. And just to make sure that it's not like I'm not pulling anything out of my sleeve here, this distribution could still occur if I encode the string of that number of C's followed by 1 A and 3 B's and 3 D's and 1 end of stream marker. But for the sake of keeping things short, even though I've just spent 2 minutes explaining this, I'm just going to use that distribution to encode a string of all C's. Okay, so let's begin. So I'm going to run the algorithm I had before. I'm going to keep going, and I'm going to output any common prefix as it forms. And actually, one more thing I'll note. Notice that C is right in the middle of my cumulative frequency table. If I were to draw the diagram that I did in the previous lecture of the real estate for each symbol, I'd have something like this. There's A, there's B, there's end of stream, and there's D, and the entire middle is C. Okay, so C is right in the middle. That's the key to this problem occurring, although we don't care that much. Once the problem has occurred, we'll sort of see what was going on here. So I begin compressing my data, and I watch my compressed bit streams. Let's take a look at low and high as I keep going. One thing you might notice is that I am not noticing any common prefix at all. Another thing you might notice as we go, I'm going to go backwards, and I'm going to go forwards. Notice that low and high are always going to begin with 0 and 1. I'm not able to find a common prefix, but watch the bit right after. Notice that low and high seem to be converging to something, but it's almost like they're converging to opposite things. So low is turning into a string of 0 followed by a bunch of 1s. High is turning into a string of 1 followed by a bunch of 0s. And at risk of turning this into real analysis again, let's think about what those strings actually mean as fractional values. So 0.111, I should be careful. 0.0111 all repeating. If this sequence of 1s goes on forever, and in fact, if I keep encoding C's, I can make it go on for as long as I want. This sequence of 1s going on forever, and this sequence, 0.10... Okay, well, what do I know about these? Okay, well, I know that 0.10 in base 2, if the zeros go off to infinity, that's the value 0.5 in base 10. And it turns out that, hey, wait, this is the same problem that I had before of 0.9 equaling 1. It turns out that 0.01 repeating is actually also 0.5, right? It's just 0.5. I'm approaching 0.5 from above and from below. And if we keep going, we'll notice that this keeps happening. And in general, I can make this go for as long as I want. I'm going to stop it here because we've seen the pattern. The issue is that there is some behavior, apparently, that's common to both of them. They're both approaching a common value, the value 0.5, but they haven't hit it yet. And eventually they will. So at the next step, if I hit the next character, in my normal algorithm, one of them will roll over. One of them will get just a little bit above 0.5, or the other one will get just a little bit below 0.5. The range will divert to one side of 0.5. When that happens, I will suddenly have a massive common prefix, and then I can output it and everything's all right. But the problem is, how do I know that will happen in time? If I encode a long enough sequence of C's, then I could end up locking up the bits of low all the way to the end. And there will come a time at which at my next step, the value of low and high hasn't changed. It's just stuck, and I'm not able to do anything with low and high. If that happens, encoding fails. So although it is actually in an abstract sense always a temporary problem, that is to say, low and high as real numbers are always different. No matter how small they get, they're always different. I only have a finite amount of precision, though, so they might look the same. And even that's not a big deal in a broad sense, because this rollover will always happen. They will eventually match up again and I'll get the common prefix. But I don't know if I have time to wait. It could be that too many bits are needed before that happens. So I need some way around this. And here's my recommendation. The name of this issue is something called Underflow. So what's happening is, functionally, this locking up of bits results in the actual functional precision that I work with slowly decreasing. As time goes by and this sequence gets longer and longer, I have fewer and fewer bits to actually work with at each step. And so it's not overflow. I'm not going over my limit. In a sense, I'm going under my limit. So it's underflow. I'm losing precision because some bits are solidifying. So we have to address this somehow, because if I'm unlucky, and this can happen for a lot of different reasons, if I'm unlucky, I could end up converging towards 0.5 like this. When that happens, it's catastrophic. If I run out of bits, then encoding has just failed. And keeping in mind, I have 16 bits, but I could be encoding billions of characters. If it happens once, then I'm in trouble. So I have to have some way around it. And what I can do is, if I guarantee that eventually the problem will go away. So basically, if I had a long enough binary representation, for this sequence keeps accumulating over time. The number of bits that's locked up keeps growing and growing and growing. But eventually, I always roll over and everything's fine. If my only issue is waiting long enough, then maybe I have a remedy that doesn't involve increasing precision. Maybe what I could do is discover when this problem is forming and just fold the number so that those bits are excluded. So right now, for example, I've got 8 bits that are an accumulating underflow problem. So what I could do is I could say, how about this? Let's just remove those 8 bits and say, okay, we've got 8 bits of underflow happening. And then I can use those bits for something else. I actually get to bring in 8 bits of other data. So I still get to keep my 16 bits of precision. And I just keep track of, oh yeah, right, there are 8 bits sort of folded out there. 8 bits that I've taken and spliced out, and I'll work with them later. When the underflow finally resolves, when low and high end up equaling the same, the first bit ends up equaling the same number, when they both hit the same side of 0.5, then just remember there were 8 saved up bits of underflow. Now another thing to notice is, okay, when the underflow is forming, low looks like 0.01111, high looks like 0.1000. Eventually, one of them snaps to the other one. So in this case, low ended up snapping over to 10000. Otherwise, maybe the other case could be high could end up snapping to 0.01111. But one of them rolls over and equals the other one. When that happens, I can finally do a shift. I output the first bit, which now matches, and I'm guaranteed that whether high ends up being 0111 or low ends up being 10000, the bit that I output, all of those other saved up underflow bits, remember that I had 8 underflow bits saved up, it'll always be the opposite bit as the first one that I output. So if I keep track of how many underflow bits I have saved up, how many I've folded out of my number, then the number of bits the bits I end up outputting when the underflow finally resolves are the number of underflow bits, and the specific value of the bit is always the opposite from the first bit that I output, the eventual most significant bit of low and high. What this is describing is, first, we don't have to wait until the problem gets this bad to fold the bits out. So I could say, yeah, that's obviously looking bad. But in fact, I could have caught the problem way back here. Okay, so here we have low and high look like this. And at this step, I can't shift out. So the most significant bits do not match. And the least significant bits, low's least significant bit is 1, high's least significant bit is 0. So at this point, I can actually already stop and I can fold out this single column. I can say low and high are growing towards each other. They are beginning to converge to 0.5. So just eliminate this column and add 1 to my counter. And at the next step, this column's already gone. Now my counter is 2. And then here's my counter is 3. So I actually just splice out 1 bit at a time. I don't have to wait until the problem becomes this bad. So what this is suggesting is, if you notice that low equals 0 something and high equals 1 something, and furthermore, you notice that this is a 1 and this is a 0, then do the following. Remember that an underflow occurred here, and just splice out x and a. So low is now 0yz and high is 1bc. And just remember for later, make a note on the side that you have one more underflow queued up. And so in this case, notice that underflow is affecting the 8 bits after the most significant bit. And when it finally resolves, I output the most significant bit followed by 8 of the opposite bit, whatever that ends up being. So in this case, low snaps over to high, but high could snap down to low in some cases. So all I'm going to do is, I'm just going to keep a counter of how many underflow bits I've snipped out, and then as soon as it finally resolves, I just output all of the saved up bits. And so if we do it here, we can keep going. Let's take a look at the process with underflow handling employed. Okay, so I'm encoding the same sequence, and I'm still not outputting any compressed bits. But notice that I'm not seeing any pent-up underflow occurring in low and high, because I'm deleting those bits as I see them, and I'm keeping this underflow counter of how many underflows I've removed. Okay, so I keep going here, and my underflow counter is now 8, and I think we're ready to snap back. So at this step, finally, low and high have a bit in common. It doesn't matter how many bits. In this case, there's actually lots of bits in common. If as soon as at least one shift happens, after the very first shift, output the bit that was shifted out, and then output underflow counter copies of the opposite bit. So underflow counter was 8, and I output a 1, so output 8 zeros. And then whatever other bits need to be shifted out. And set your underflow counter back to 0 so you can begin piling it up again. Because of the unique nature of this computation, so we can't get infinite precision in finite bits, but we don't need that for this because there's only a certain kind of precision that we require. We just need enough room to move between low and high that we can do one more step of our calculation. And between being able to shift out the common prefix and save up underflow bits, keeping in mind that we can't save up an infinite number of underflow bits either, because our counter might be, I don't know, an int or something, so maybe we can save up 4 billion underflow bits, but that's still quite a bit. That gives us a huge amount of precision to play with. That we actually get enough precision that we can do arithmetic encoding, where there's still numerical error because we're still working in a finite number of bits, but the numerical error is so far down on the other end. It's so far away from our probability values that it's not likely to have an appreciable effect on encoding efficiency, but certainly not on the validity of encoding. So the encoding is always reversible with this approach. We also have to make sure, just to be clear here, we have to make sure that our total cumulative frequency, t, is of course going to fit in the number of bits that we use. So if I've chosen to use 16 bits, then it really needs to be important that my cumulative frequency, which is in most cases, the size of my input, is at most 2 to the 16. But you could argue, wait, I might want to encode a billion things at once. I don't want to have to break them up into blocks. What do I do then? Well, it turns out if your cumulative frequencies get too big, you can always scale them all down just to make to bring that introduces a small rounding error to your probabilities. But you need to make sure you bring the total cumulative frequency down to below 2 to the 16 or 2 to the whatever number of bits you're using. And you can do that by scaling. You can do it by using a larger number of bits. So here is the encode pseudocode using our approach. And I've written, so this is, for example, a bitwise OR. I've used C-style notation for the pseudocode. It's a bit ugly looking. I'm actually going to post a C++ implementation of a basic arithmetic encoder using a fixed probability table. So you can look at what we have to do. It is this. I transcribed the pseudocode from my C++. I guess I have the same typo that I had in part 1. I'll have to fix that. And then all we have to talk about now is the decoding process. So in the real valued algorithm, decoding basically was the same as encoding with one extra bit at the beginning of each step to figure out what the next symbol was. And once we know what the next symbol is, we just run the encoding process to catch up to it. I'm not going to go through a full example of that, but there are 2 additions that we have to make. So the first thing is we have to keep track of our encoded value. Remember that when we decode from arithmetic encoding, I've given you one number, and I've said figure out what encoding corresponds to this one number. So you have to maintain that. Now, of course, when I send you that one number, I might send you a bit stream of 40 billion bits. It turns out all you need to do is keep track of the first queue of those bits. It has to be between low and high. And if low and high can be stored in, let's say, 16 bits, so can your encoded sequence. Every time you shift a value out of low and high, you shift the value of your encoded thing. And so it's called, this is actually supposed to be rendered in like a courier font, but it's called encoded. You shift it every time you shift low and high. When you shift low and high, you shift a 0 bit into the rightmost position of low and a 1 bit into the rightmost position of high. What you shift into your encoded value is the next bit from your encoded bit stream. Whenever you splice out a bit from low and high to handle underflow, you do the same thing to your encoded value. And then you bring in the next bit from the encoded bit stream to fill the rightmost position. The other thing is the equation that you have to use to compute the next symbol is this horrendous mess. It's the same equation as would have appeared in the real valued version, but it's been adjusted in a lot of ways to account for the funny fixed point arithmetic, and as we can see, these plus ones and minus ones to account for the way that the high value works, which comes out of nowhere. In preparing for this course, I've spent lots of time making slide diagrams. I've admitted before to the horrendous amount of time I spent doing that. In terms of a conceptual thing, I probably spent days just trying to figure out exactly why I can justify all the plus ones and minus ones. I tried all the permutations of this equation without the plus ones and minus ones, and none of them work. And it turns out, although no book seems to give this explanation directly, it's very simple. It's because high is not the actual upper endpoint of the range. And although I knew that at the time, reading the formula that the book just says, oh, use this, without giving any explanation, was still pretty infuriating. So we talked about in the encoding process for this variant, I've said, let's have the compressor, to avoid emitting extra bits at the end, assume that there's an infinite sequence of 1 bits past the end of the stream. We have to do that with a decompressor as well. If you reach the end of the encoded bit stream, assume that there are just a bunch of 1 bits going on forever. And so if you need any more than there are, you can always get them. You still need underflow handling in the decompressor, because obviously you have to mimic the encoder's behavior. But because you're not outputting a encoded bit stream, you actually don't need to keep an underflow counter. You just need to splice out all the bits like you normally would, and then throw the bits away. There's no need to keep them for later. So here's the pseudocode for that. And there's a lot going on here. So I'll post an implementation of this for a basic probability distribution. We'll find out in the next lecture that the reason we care so much about this process is not because this is necessarily, we don't need to spend too much time playing with this. I would say the state of the integer arithmetic encoder is pretty solid these days. There's not much we can do to improve upon it. We need one because we need to do arithmetic encoding, because arithmetic encoding enables an amazing way of increasing compression and allowing us to introduce finally some ability for dependencies to exist in our data and still get really good compression from the entropy coding stage. Something that Huffman coding can do, but it's much heavier weight to do that. And what I'm talking about is the ability for the probability of each symbol to change between each step of encoding. And that's what's called adaptive encoding. So now that we know that we can implement arithmetic coding, we can finally begin talking about adaptive methods.